No, till now, no.
Okay, okay. It's okay.
So, do you have any doubt?
Uh, I think I was waiting more for the content of the session, and then take it from there.
Okay.
So more or less, I was looking forward to whatever lecture you have prepared, and then we'll go accordingly.
Yeah, but only one student has joined. Only you have joined. Eh,
I'll try not to disappoint you.
yeah, okay. Okay, even I'm looking in vote also. Only one person have vote. I think you have only voted. Is it?
No, no, that won't be me. Um, I have not voted in the poll.
Okay. Okay, I'm sharing my screen. We'll discuss. I don't have any slide, but we'll discuss something in quickly.
Okay, I can see your screen.
Yeah, thank you. So in week 7, things are related to eigenvalues, eigenvectors. So in week 7, introduction, inverse, power matrix, invertible, inverse, power matrix, the determinant is there. So in week 7, I started eigenvalues, eigenvector, and then existence of eigenvalues, using determinant, algebraic multiplicity. Okay, special case eigenvalues. Computer based. Okay. So have you gone through with the content of week 7?
It's strange actually because whatever contents are listed for week 7 have been discussed in the sessions for week 5 and week 6 already.
Okay,
So
one minute.
it's kind
These
of
are listed. Okay, okay, one minute. Whatever is listed here, it's already discussed in week 5.
the week 5 session we had quite a bit of discussion over eigenvalues and eigenvectors, and then
Okay, can
week
you tell
6
me
we
what are
had
the topics are there? It's showing in your.
I'll just check and get back to you just a second.
Yeah. It's updated syllabus actually. This is May 25. I don't know. One minute. Yeah, just let me know.
Better I'll just share my screen and you can see
Yeah,
that.
yeah, that would be good. Let me stop sharing. Once I will get the what are the topics, then we'll quickly.
Right, so I think you can see my screen now.
Yeah,
See this? This is week 5 right now. I'm showing you.
yeah.
This is week 5, and all this discussion was there. Then we started on eigenvalues and eigenvectors and
Uh,
discussed quite a
yeah.
bit about it.
Just show me the week 7 first. Let me, then I will tell you the differences.
Huh. And then there is week 7. So
Okay.
eigenvalues and eigenvectors
So same
existed.
it. Then it is fine. Then whatever I'm saying, I will tell you what are the differences there.
Okay, fine. Please go ahead.
Actually, there is a slight difference. I thought maybe the syllabus updated.
Okay, okay. Please go ahead.
So the differences there and here is not more only the dimension case. So that is what. So whatever you looked up here, eigenvalues, I think this is going to be for 2 cross 2 matrices. Yeah. This
Right,
whatever
we were writing quadratic equations. That's correct.
yeah, only for quadratic equations only till R2, no? So that is what I think. Yeah, I was taken from the starting, and I left in between, and then now again I have started going to start. So I'm going to take the session. So I in a starting I said we are going to see the content. It is a kind of, first we will look at the content which is over R2, means either could be R2, or maybe we'll deal with the matrices if it is 2 cross 2 for the, not if means we'll deal first the matrices of 2 cross 2. Then later we'll discuss, means whatever we are discussing here in the week 7 going to discuss in here, this is going to be for n cross n, for any order of the matrix. So that's why the definition is not going to be changed. Even I will say even a bit, even everything is same. See now here the differences you can see, the matrix is given over n cross n. Either could be more than, so either could be of 5 6 or maybe means more than 2. That is what everything is going to be same. So then it is fine to discuss from your side, no? So you know the eigenvalues, right?
Right. Eigenvalues are uh, essentially, we are writing matrix minus lambda I, and the
Yeah,
polynomial we are getting when we calculate the determinant of that, we are solving it to 0. And
yeah,
what we are getting over there, the solutions of that polynomial, those are the eigenvalues.
yes. That is exactly. So here if you see, exactly what the professor is discussing. No, no. So he's just giving the definition first. So what it means, that can you tell me that also, uh, the cases, what is the use of then eigenvalue?
Once we have our eigenvalue,
Yeah.
we can write up the matrix
Hmm.
by saying that matrix minus that particular eigenvalue. Let us
Hmm.
call it lambda 1. So we'll call it A minus lambda 1 I, and then
Hmm.
we get a new matrix. We
Hmm.
find the we find the eigenvector associated
Hmm.
with that matrix,
Yes. Yeah. So
and
why we are finding the eigenvector? Do you have idea exactly? So whatever we are going to do today discuss, or why whatever we are discussing, that is the same. There is no even even I will say the slightly difference, even exactly same. So whatever you are saying and whatever here in the content are the same. So what is the use of eigenvector?
see the eigenvector has a property where when we use the matrix A to transform the eigenvector, we
Hmm.
don't change its direction, we only scale its length. So
Scale its length. Totally
right,
fine.
we
Yeah.
make it short or long. So it
Long.
has that property, and
Yes.
using the set of eigenvectors, we can form a basis for the column space of the matrix, which is very useful.
Yeah. Yes. That is what it is going to be. So in the terms of matrices, what you can use to find it? In terms of matrices, how we can use this eigenvalue eigenvector to do something?
So then we once we have found the basis for the column space,
Yeah.
every vector in the domain that will be transformed by the matrix, it
Hmm.
will end up as a linear combination of the eigenvectors. That is what we get finally.
Okay. Okay.
Is all that okay?
Yeah, everything is totally correct. Yeah, everything is totally correct. So that is what I was going to say, that what is the use of, you already know it. So the mean to say, once you have a matrix, so I am not restricting you. You know it already for 2 cross 2. Only I am changing here, no, n cross n. So in place of, let me write for 3 cross 3, or maybe 4 cross 4. Okay, everything is same. So you have a matrix of order 4 cross 4. Okay, and then this is, in the see, the columns are, we have like a vector, you can think of R4, right? So, or we can say, let me, I am taking a vector from R4, okay, and multiplying by a vector. So you, what you said, by sudden I got a vector which is behaving like a just scaling up and down. I'm not changing any direction. There is no change in the direction, but only just it is scaled up and down. So this kind of vector is called eigenvector, whatever you just said. So this is true for any general matrix. It is, we are not sticking till 2 cross 2. It is true for any general, any order of the matrix, 4 cross 4, 5 cross 5, or any square matrices. And these vectors are called eigenvectors. So we know, right? We know that we have a, let's say I have a linear transformation from vector space in higher dimension. Here is R4, I'm writing R4 to R4. So again, the same way we know, right? A matrix, or sorry, a linear transformation we can write in the matrix format, correct? Is it true?
Right, we can write a
Right?
transformation.
Yeah. So either, let's say some expression is given for this t, okay, some expression is given, means here the properly expression we can write in the matrix format. So suppose I, again the same case here, I'm getting a vector v from R4, where t of v is again we having like a lambda time v, means t is exactly behaving like a matrix, no? So it means this is the one correspondence here in the matrix format and the linear transformation format, correct? So in place of
Right,
doing
that is
this,
okay.
this is tv is equal to lambda time v. So here this vector is called eigenvector. So whatever you learn in 2 cross 2, there is no change here. Okay, there is no change, everything is same. So you know already what is the eigen value here. Okay. Okay, so what is the next thing is that you said already will form a, so we'll get, so like this we get here, let's say, we'll do what, let's say I have a matrix of order 4 cross 4. Okay. And now we will do a kind of lambda time identity matrix, and we'll find the determinant and equal to 0. This is, you are saying for 2 cross 2 it will, we have the same exactly. We'll find the eigenvalue by this way. We have a 4 cross 4 matrix, we'll proceed like this. Okay. And we'll find the not, you got their quadratic form, but here we'll get a polynomial of degree 4. We'll get a polynomial of degree 4. If your matrix is of order 3 cross 3, so if we have the same case identity, okay, let me make it bigger, identity, and you will find the determinant equal to 0, you will get a polynomial of degree 3. So whatever the order is there, you will get the polynomial which is equated to 0, and you have to find the root of that, and that order of the polynomial is going to be the whatever the order of the matrix. So as the same case you learn for 2 cross 2, you'll find like this, and determinant equal 0, equal to 0, you will get a quadratic equation. Something would be there, something would be there. So whatever the order is going to be, the same order is here exactly. And by this way you will find the some roots. So let's say I'm finding the roots lambda 1, lambda 2, lambda 3, lambda 4. So now tell me some properties you know already for 2 cross 2. So ever you heard algebraic multiplicity, geometric multiplicity
Right, we had discussed those things.
in the
Uh,
2 2, correct?
right, so it simply meant
Hmm.
number of times one particular eigenvalue shows up in the roots is called algebraic multiplicity.
Algebraic multiplicity.
So if it's like lambda 1, lambda 2, again lambda 1, and then lambda 4, then we
Hmm.
say lambda 1 has an algebraic multiplicity of 2,
Hmm.
lambda 2 and lambda 4 have 1 each.
Hmm. Yeah. Yeah, so that is exactly the same. Here is also, if the roots are repetitive, means you are getting the lambda well, lambda 1, lambda 2 are same. So whatever you are saying here is also the same. If it is some repetitive roots is coming, then you can say the algebraic multiplicity is that many. That means that much. And yeah, geometric. What is the geometric multiplicity now?
That will be the number of eigenvectors
Hmm.
associated with that particular eigenvalue.
So number of eigenvectors, or that is not proper word. Number of independent eigenvector.
That is correct. Independent eigenvectors.
Independent word you cannot miss. No, you cannot miss it. Miss that, because there for one eigenvalue you have infinitely many eigenvector. Correct? Or you know it?
And we can just scale it and generate
Yes.
as many as we like.
Yeah. So for one eigenvalue you have infinitely many eigenvector. Means you can say for one eigenvalue you can generate a eigenspace which is a subspace. Correct? But saying to be the main important related to the geometric multiplicity, when you have a for one eigenvalue you are getting two different in the sense that two independent eigenvector, two independent eigenspace, you can say, not independent meaning of space, two independent eigenvector. Mean to say you'll for particular eigenvalue, let's say I lambda 4, which is of, let's say its geometric multiplicity is 2. Okay. And suppose the geometric multiplicity is 2, and you started finding the way, right? You said no, you a minus lambda I will do, and let's say here is I'm substituting I, sorry, lambda 4, and we'll solve a system of linear equation, correct? And by this way we'll reaches to a, will reaches to a system where it have infinitely many solution. In the case of two independent solution we'll get, right? I mean to say, by this way you are solving, by this way you will solve, and then you will get a two independent eigenvector, let's say v1 and v2. Suppose you, while solving this, you end up with unique solution. Not unique solution, it is not unique solution. You end up with only one one free variable, it is called, you do you remember one free variable? Hope you able to relate it. Do you remember it?
So one free variable simply means that all the other variables can be written in terms of this one variable.
Only one, yeah. So that means it will generate only one vector, right? It, by this way you will get only one vector. If you have a two free variable, that means two independent kind of eigenvector it will give. So if it is giving two independent, that means for this eigenvalue you have a geometry, sorry, yeah, algebraic, sorry, I wrote, wrongly wrote here. This is algebraic multiplicity. Sorry. Suppose for this I lambda eigenvalue you have algebraic multiplicity 2, and while solving this you got that you have two independent eigenvectors. So this is called geometric multiplicity is 2. So by this way, there is a relation between a algebraic multiplicity and geometric multiplicity. Can you tell me that? Hope you remember.
So algebraic multiplicity will
Yes.
be greater than or equal to the geometric multiplicity, which will be greater than or equal to 1.
Yeah, exactly. Yeah, this is the what it is. So if you have suppose you know, so you are able to everything related, so everything is fine then. If it is only one algebraic multiplicity for this eigenvalue is 1, so that means geometric multiplicity is anyhow going to be 1, because for one eigenvalue you will get a one eigenvector. The problem is when you have a repetitive eigenvalue, then there is a possibility that either it could be that many eigenvalues or maybe lesser than. Suppose for this one, let's say, or even for the, yeah, let's say now again the, let's say r4, so lambda 4, it have 3 eigenvalue, algebraic multiplicity is 3. So there is a possibility that it have, it could have only one, or maybe two, or maybe three eigenvectors separately. So it's depend on while solving, we'll get those all when we start solving this system of linear equation, and depend on the free variables means, we hope you know how to get it. So when we start solving, we'll reach us to somewhere, and from there we'll start getting independent vectors like this. So when solving we'll get, okay, if it is 3, then we'll say that geometric multiplicity is 3, and if it is 2 we are getting the geometric multiplicity is 2. But it will never happen that if it is 3 here and you cannot get 4 independent eigenvector, it will never happen. So that's why this constraint is there. You can put the constraint, that upper bound. So here is algebraic multiplicities are always greater than or equal to geometric multiplicity. So already you know the concept of this one, algebraic multiplicity, geometric multiplicity. Okay, eigenvalues you know. So that is what it is. So what is now remain? Uh, let's say I have let me solve one example then. Let's say I have this matrix. Now see, this is a 3 cross 3 matrix. I want to find the eigenvalue of it and eigenvector. So what you will do the next step? here?
So we will write along the diagonal 1 minus lambda, 1 minus lambda, and 1 minus lambda. And
Okay.
then we'll calculate the determinant.
Okay. So you can let's solve with me and let me know the things here. So what is going to be now here?
So we'll expand along column 1 because we have less number of elements over there.
Yes.
So we expanding along column 1, we can just take that and write uh, 1 minus lambda multiplied by 1 minus lambda whole square.
Yeah.
And then the next one is again the 1 on the bottom. So that one will be 1 minus lambda. So which will be just plus lambda.
Yeah. So which will be just plus lambda. So finally this is plus lambda. This is equal to 0. Correct. Yes. So now we got here 1 minus lambda cube plus lambda is equal to 0. So here is 1. So can you tell me the expansion here, or any other way we can find the lambda value?
Personally, I don't feel very good about expanding it because I don't know what we'll get over there. Is there something we can do to this expression itself?
No, so that is what the professor don't want to do like this, because he didn't taught the the thing is he didn't taught the polynomial and how to find the root. So surely some hint would be given here that okay, some particular number is going to be at least one eigenvalue, so that you can substitute and you can reduce in the quadratic form, and he taught at least till quadratic form. So for this, he then I think in this video only have started a very specific kind of matrices. So no need to even proceed with the further, because if you proceed, because we have to find the root, but you don't know how to find the root, so there is no mean to proceed. Let's say at for the time being we got some lambda 1, lambda 2, lambda 1, lambda 2, and lambda 3, and again we'll solve the system of linear equation, we'll see it. But let's see the trick. I think it professor wants to use some trick, because here we don't proceed with now. So you see, now everything is the same here, the meanings and all. So he's just defining. No, I said no, for the matrices. In the lecture, his professor is connecting with the linear transformation and the matrix. That what is the meaning of that is what I said. No, if you have a matrix, sorry, linear transformation, it's we have exactly in the matrix format. So either we are dealing with the matrix or with the linear transformation are going to be same. So he is the see the same a minus lambda. I proceed with that. What is going to be there? He just the words are there. So have you gone through with the lectures? No.
No, I have not seen this lecture.
Okay, 1 minute. Am I audible?
Yes, you're audible.
Okay. Okay. So there is one property. So in the lecture, what the first lecture is professor is discussing, if you have a linear transformation from a particular space to another is the same space, then in that case you will get a vector, and if you will do t of v, it will give some the scaling up, and the same is everything is defining. So in place of, or to get this what is the exact eigenvalue, then you can do that t of v minus lambda v, or in the different word you can see t minus lambda identity, and v is there. So mean to say he is what he is in the week, like in week. So in the lecture one he is discussing. The second thing is in the lecture two, we said no, if you have a matrix, we'll proceed. Let's say for this t, the matrix is this one. Okay? And we'll get a equate. So here is equate to 0. We'll get a polynomial, and will equal to 0. This polynomial is of degree 3. Okay. Let's see, here I am writing 3. Okay. And we'll get the roots here. And that is going to be the eigenvalue. Correct? This is what the till now we know. Right?
Right, that's okay.
But the thing is that one important thing that is called fundamental theorem of linear algebra is that here is not fundamental theorem of linear algebra. What is the naming it? Also fundamental of, that is the fundamental theorem of algebra. That is the one root is that, that is this is called some theorem it is. I'm just forgetting the name. What is the name of some name is there, fundamental theorem of Some name is there, I'm just forgetting what is exactly there. So if you substitute, means, suppose you have a polynomial of lambda 3 plus lambda square plus lambda 2 lambda plus 1 is equal plus 1 is equal to 0. Let's say this is the polynomial. So what you will do, if in place of lambda, let's say I'm writing this matrix A itself, means you will find the A cube of the matrix, A square of the matrix, 2 times the matrix plus I in place of this one, means here it's telling you can think the identity matrix. If you do like this, you will get a zero matrix. This is what, I mean, or in different word, if you in place of lambda, if you substitute t, okay, and t square plus 2t plus identity, and you find the image of any vector, you will get a zero image. So this is the meaning of it, that what is the professor is discussing. This polynomial is not simple polynomial. If you substitute in place of lambda a or t, so for the t case, the whatever the expression you will get, right, this is a composition, right? Are you able to catch it or not?
Right, so it's T compose T, and the cube is T compose T compose T.
Yeah. So here is a T compose to it, means thrice it composed. So whatever the expression finally will get, whatever the any, if you do any with respect to any vector, you will get a zero image. So this is for the linear algebra, sorry, linear transformation case. This is true for the matrix case. Means here if you do the three time multiplication with the same matrix, similarly square, similarly 2a plus identity, you will get a zero matrix always. This is the meaning of this particular lecture. This is what he is saying. This fundamental theorem is of algebra, that it have always a root. So already. So this is what the professor is substituting here. If you substitute, you will get a kind of this one. You will always get a image zero. So that is what he is discussing. And this is what it says. If you have a fundamental theorem of algebra says always have a root, so you'll always get a, either it could be a complex number or it could be a real.
And that simply comes from the fact that the null space always has the zero vector in it. So
Yeah,
even if nothing else is there, the zero vector, the origin itself is part of the null space. So one solution there will always be there in some sense.
always be there, right? So I think in the next lecture he is giving the way how to find the eigenvalue. So that is what he is trying to connect. So actually I'm trying to find the trick. If it's not exactly so, I just wrote a very tedious matrix, so that's why we are not able to get it the root exactly. But no matter, very big matrix we'll see later. Some properties, using some properties you can easily do. If you are able to do easily, then it is fine. If not, then leave it. I was so the thing is, the question very less chance to come such that where you are not able to do the fraction, like here. Also, we are not able to do such fraction easily. So such kind of case is very less. Either it would be a diagonal or a kind of simple matrix, so that you can easily factorize it and get the root. If not there, then a simple matrix, a very specific format is given. I think professor will discuss in let's see then in which lecture. So this is the example he is solving in this lecture. So are you able to catch all or not?
So I think he is showing us that there are certain cubic polynomial equations where we can get a root by trial and error, and the root
Hmm.
is not very difficult to find. We put, we
Even
put
not trial
-1,
and
we put
error.
-2,
Even not
we put
even
something
not
something.
trial and error. Even not trial and error. We can means it's look like very simple. We just take the lambda common and then it will easily convert in the quadratic form and then you can easily find the root. So it is not a trial is not he is showing you one trial is then you can do, but if many because he didn't taught the trial thing. Here is here very specific matrix is there. See there, this is a diagonal matrix. So roots are going to be the same whatever on the diagonals. So specific matrix is either could be a so not diagonal. This is not diagonal matrix. I mean sorry, this is upper triangular matrix. Similarly, maybe a diagonal matrix. And there is a some maybe in let me see in the next. So I think this is whatever the very specific matrix of any order with some of the row particular row or some of the all rows is some fixed number is eigenvalue. So he will dot later. Those special kind of matrices we'll see later. So till here week 3 is lecture 3 is discussing the eigenvalues, eigenvectors, some one fundamental theorem, use of the algebra, fundamental theorem of algebra. And then third lecture he's discussing how to find. He's just giving the matrix substitution and the road which we have discussed it. In this fourth lecture, algebraic and geometric multiplicity. So this seventh lecture is for only the extension. No basic theory is not no new basic theory. So you know already the algebraic multiplicity, geometric multiplicity. So can you connect me one thing with the eigenspace? Ever you heard?
Eigenspace is basically the space spanned by the basis of eigenvectors. That's how I understand it.
Okay.
Is that okay?
Yeah, it's fine. But oh, yeah, that is totally correct. Spanned by the eigenvectors. But let's say I have a matrix and I am doing like this a minus lambda I. Let's say eigenvalue is lambda 1. Okay, and by this way we used to find the eigenvector, right? A minus lambda I or lambda 1, then I, and we solve the system of linear equation, correct?
Equated to zero, yes.
Equated to 0. So what we are doing here particularly, let's say we have this is a 3 cross 3 matrix. So what we are doing particularly, what we are finding, what kind of solution we are finding, or of which matrix we are finding the solution?
So we are finding the null space of A minus lambda 1 I.
A
That's what we are
minus
doing.
lambda I, yes. So I can okay, so let's say this is the particular matrix. Let's say I am saying this matrix P, this whole bigger matrix A minus lambda 1 I is P. So this is a kind of homogeneous system, right? This is a homogeneous system of means this is a homogeneous system and we are finding the null space of it, correct? So means solution is a null space, correct? Solution is a null space. So here is let's see, the solution is null space means here whatever the this matrix is there, we are finding the solution which is a space. So that is what here in the case his professor is discussing. We are finding the null space which is nothing but the eigenspace, eigenspace of this matrix A with respect to lambda 1. This null space is nothing but the eigenspace, and whatever the dimension of it, whatever the sorry, whatever the basis you will get for this one, basis of this eigenspace, whatever the basis you will get, this basis is you can say the particularly you will, let's say the basis element you found, whatever the dimension or whatever the vectors you will get, independent vectors, that vectors you can call the eigenvectors, or all vectors are eigenvector of this space, but particularly independent eigenvector you can get in the basis. Are you getting it? Are you able to connect it?
Right, basis must always have linearly independent vectors.
Independent
Otherwise,
eigen,
it won't be a basis.
it won't be a basis. So the whatever the vectors will come, those vectors are going to be the eigenvectors of the this matrix A, and independent eigenvector you will get. So can you tell me, if you have a lambda 1, which is the geometric multiplicity is 1, so what is the dimension of the eigenspace of lambda 1? Can you tell me?
That is one, just one vector.
That is one, exactly, because if geometric multiplicity is one, so in that case we'll get one eigenvector. So you said no, eigenspace is just spanned by the one eigenvector. So base, so by that way dimension is one. So you are getting, yeah, good. So here that's all. So if you have, let's say I have lambda one, where which have the geometric multiplicity, sorry, not geometric. Why I'm writing the geometric always? Algebraic multiplicity. Algebraic multiplicity is, let's say, 3. Sorry, I'm always writing even I'm speaking also I'm saying geometric multiplicity.
That's okay. I understand the difference, so it's okay.
But no, later people will see, then may get confused. So here is mean to say algebraic multiplicity. So let's say I have lambda 1, which is algebraic multiplicity is 3. So can you tell me what is the dimension of the eigenspace of this lambda 1?
We cannot say immediately. We'll have to solve first, and then we'll have to see how many free variables we are getting in that
Hmm.
null space homogeneous equation. And
Hmm.
depending on the number of free variables we have, we'll be able to construct some vectors. It may be one, it may be two, it may be three.
3.
So depending on how many vectors we are able to get as the basis of that null space, that will
Correct.
be telling us how much the dimension of the eigenspace of lambda 1 is.
Exactly. Exactly. That is what, yeah, exactly. So this is what the professor is discussing. So that is what it's happening. Everything, everywhere is here. So, so now is it clear to what is the distinction here in week 5 and here is? What is the differences? No differences. No differences is there. Only the dimension of the matrix is changed only. Correct?
One important difference is there in the uh, week 5 we had only quadratic polynomials which you can always solve without any problem. The moment
Hmm.
you go to cubics you may not be able to solve, so that difference is important. Let's see that. Let's see what he has the professor has shown as the trick and other things, I think.
So actually, even the whole lecture professor is trying to avoid it. Yeah. So for very critical polynomial, so he is trying to say most of the time try to provide or give such matrices which have easily we can get the whatever the polynomial we are getting, characteristic polynomial that is called, and that's characteristic polynomial very simply could be factorized, or maybe we can provide some eigenvalue between that so that people to factorize easily, means they have some hint at least, means the
Right,
student
so
get
if we can get one root of the cubic, then we have reduced it to a quadratic. So
quadratic. Okay. So this is what here computing by hand. So everything. So this is the first lecture, no? So 8, 9, computer. Yeah. Rest all we'll discuss in the next session because now 4 is done. By hand is the same thing is there. Column space, null space. We'll discuss in the next. Special case of complex eigenvalues. We'll see what are the things in the. Yeah, this is what I want to discuss. It is in the next session. We'll discuss it because half of the will discuss in the. Otherwise, tomorrow will. So tomorrow is going to be one session, no?
Yeah, I think there is one session tomorrow.
Yeah.
Maybe you can give a primer at least, since we are here and we have time.
Yeah. So primer means what are the things are there? What is going to be
Right, some general example of what we can expect.
in the next session? This sorry in the next
Uh,
lectures.
what is the remaining content of the next lectures? Maybe if you can give me a little
So
primer.
okay. So in the remaining content by hand is the same. He is means he's just explaining that what he how he will solve. This special case is good one, which is very handy also, and many times it is very useful because you don't need to do a minus lambda I. Means here what is happening here, you will get a suppose you have a matrix of this case where the each row if you sum up means suppose I summed up I got 3, I again summed up second row I got 3, I again summed up I got 3, means each row when I am summing it I am getting 3. In that
So the
case
sum of the individual elements is the same for each row.
individual yeah row is going to be the same for each. So in that case that sum is actually the eigenvalue. This particular this 3 is going to be one eigenvalue of this matrix. We only get one, at least only one will get. This 3 is going to be one eigenvalue of this matrix. And the eigen what is going to be corresponding eigenvector? The corresponding eigenvector for this one is going to be 1 1 1 1. Very simple. 1 1 1 1. One means whatever the sum I am getting, that sum is going to be eigenvalue and corresponding eigenvector for that is going to be 1 1. And the second one important is that suppose you have a matrix where where the entries are like this. Let's say let's say some entries are filled. Let's say a particular, let's say at third row and third column. Okay, at particular at the third row and third column, every element, let's say this matrix is of 5 cross 5. Okay, rest all here is only non-zero. Let's say 3 is here. At particular third row and third column, it is going to be non-zero, and rest all, I don't know what is here. It doesn't matter. I don't care about it. It matter only the third row and third column. Even you cannot say third row and fourth column. Okay, don't change it. Means see, this is going to be same. Fourth row, fourth column. Fifth row, fifth column. And the specialty of that column or that column is going to be that column is going to be only at there is non-zero and rest all zero. In that case, this whatever the non-zero you are getting, that is your eigenvalue. And here it is 3 is there, so 3 is going to be eigenvalue. And corresponding eigenvector is going to be 0, 0, 1. At the third place, it is going to be 0, and rest all is going to be 0. Sorry, non-zero, and rest all is going to be 0.
So in the matrix itself, in that particular row and column, only
Yeah,
the diagonal element is non-zero,
non-zero.
and the
Only,
corresponding to that
only
diagonal
the
element.
particular. Maybe here is non-zero, here is non-zero, even the some other is non-zero or zero. It doesn't matter. Only that particular row, that particular column is have this property. In that case, it is going to be
Column only, or even the row should also have zeros?
no. Only the column. Column is enough. Column
Okay,
is
so
sufficient here. This is what here. When ei is an eigenvector of A, this is what it's going to be. Ith column of A is ei. Means here is if your eigenvector is going to be, in that case it is ith column of A is ei. The eigenvalue is the constant one. The column is only the matters here. And here is the first one is all row sums are the same. In that case, the eigenvalue is the row sum, and this is one very good. Even so many in this lecture will so many important properties. So many important properties. The inverse of the eigenvalue of the inverse matrix. So many beautiful. So this lecture is very good. Even maybe, yeah, maybe some maybe in some other lecture happened. So these lectures are very good and important, very important. Sometimes, if you have another properties of the eigenvalue eigenvector is, let's say I am saying, let's say I have a matrix A which is invertible. Then lambda value eigenvalue or eigenvalues are the lambda 1 lambda 2. In that case, the eigenvalue of A inverse is 1 upon this sorry, yeah, yeah, 1 upon this. And what about the eigenvector? Eigenvectors are going to be same for this one also and for this one also. Let's say this eigenvector for this one is v1, then for this eigenvalue is also v1 for the inverse case. And some another property of the case is that when you have a matrix A and S is an invertible matrix, so eigenvalue of S inverse S, okay, for this one is your lambda, so for whole one is also going to be lambda. Are you getting it?
so this formula is the one we are using for diagonalization essentially.
Diagonalization, correct.
So we are saying that the eigenvalues of the diagonal matrix will be the eigenvalues of the whole thing, and that we can show by the determinant properties, because when we write the determinant of S inverse and S will cancel each other out, and only the
Hmm.
determinant of A will remain, and that's how we are showing this, I
Yes.
think.
So then there is one next property. A and B is there, and let's say suppose or BA is there where B is invertible. B is invertible. A have lambda eigenvalue. So in that case, the eigenvalue for this one is going to be same, and eigenvector is going to be the B time lambda. Sorry, V time V is there. Whatever the eigenvector is V, this is going to be. Let me check once. I think this is the property. So very interesting properties are going to be there. Good properties. I think it is in the next algebra and algebra case it is. These two lectures are beautiful and always be useful.
7.7 and 7.8.
Yeah. See some other properties, so beautiful properties. Some of the eigenvalues means sorry eigenvector, sorry, two matrices we are summing them. Then what is the possible eigenvalues, eigenvectors. So these lectures, before to join the session or to come the session, I encourage you to see once this. These are beautiful and important properties. So many important properties are there. No, I think this is not there. This is not the case. This one, not this one, is there. So one is the, if you have matrix A, we are you are finding a power k, so corresponding eigenvector, sorry, eigenvalue. So not corresponding, the eigenvalue of a power k is going to be lambda to the power k. So beautiful, yeah. So at least whatever the thing is that if you are skipping, but please watch these two lectures are important. Yeah, this is a beautiful and always be useful to you. Always, when even whatever till now, even the upcoming now for any courses even, or where you are using linear algebra, or in the upcoming like weeks, it will help you. It will help you. Or maybe you may get some bigger matrix, but some tricks should be used. This kind of tricks may be used so that you can easily get the eigenvalues. You don't need to find a minus lambda I, do the find the I determinant, then find the root. We are able to do, but before to proceed for such case, the longer case, longer method, best way is to use the tricks. Sum them, are you getting same? Or maybe some of the row is, but some particular column have some special property, or maybe inverse case is happening. Some beautiful possible scenario would be there surely in the matrix, and you can apply and just read up to find the eigenvalue and eigenvector. Don't be sorry, read up with the bigger method. So this is a good thing. Always be useful.
So basically, we avoid forming the polynomial equation because it can
Yeah.
be very hard to solve, and
Yes.
do something which we know will get us a solution based on established methods that are already available.
Established method is already available. Correct. Okay. That's all.
Okay, thank you. Although I must confess to you, I'm not sure if I'll be able to join tomorrow because I'm kind of traveling. So,
Okay.
but I'll definitely watch the 7.7 and 7.8. That much I
Yeah, yeah,
know.
sure. You will surely get it and beautiful. No need to even help to get from the any. Means no need to, even if you're not joining the session, that not much, because these are just a practice. Professor even solving itself in the session, like a live session. So he's doing already in that. So if you're not coming to the session, that doesn't affect much to you.
So in the lectures, it's mostly problem solving with the techniques.
Yeah.
Okay. Okay. Thank you.
Thanks, Rajiv.
Okay. Good night then. I'll-
Yeah. Good night. Good night. Your name is Tanjil, right? Tanjil.
Yeah, Tanzil.
Yeah.
That's right.
Good night, Tanjil.
Yeah. Good night. Thank you.
Yeah, thanks.